Hello everyone, and welcome to the 10th lecture of the Introduction to Media Engineering course. In this lecture we're going to continue the topic of compression that we started last time, and we most probably are going to move into the next topic, which is on audio. So last time we talked about JPEG compression, if you remember, and we said that the idea of JPEG compression is that it can discard or at least attenuate the high frequencies. We said that we use discrete cosine transform in this task, and there was actually one slide that we haven't covered that I'm gonna talk about later. So what we said is that in JPEG compression we divide the images into 8 by 8 pixel squares. We apply DCT to each one of them, and then we do this for quantization. If you remember, we said that the low frequency or the low frequencies, they can have values between 0 to 55, so they keep their original values. Slightly higher frequencies are only given values that are divisible by 4, meaning that instead of representing them with 8 bits, we're representing them with 6 bits. And then the highest frequencies are given values 0 or 128, meaning that you can represent them just with 1 bit. 0 would represent 0, for example, and 1 would represent 128. So this is how the JPEG compression reduces the number of bits needed to represent the frequencies. Now, this in itself will actually save in terms of storage. However, there are actually other steps that are taken within the JPEG compression to get actually more compression. So this already will cause compression, as we explained last time, but let's see what else. Okay. So we say that this quantization process reduces the space needed to store the image, but it results in loss of information, as we explained. But luckily, this loss in information is not something that we will actually perceive. Now, the other step that is done within the JPEG compression that actually causes more compression is as explained here. So after quantization, there will usually be many zero coefficients, and these are encoded using the run length encoding, if you remember that we explained in the beginning, using a zigzag sequence to maximize the length of the runs. So what does that mean? So let's imagine how the after applying DCT and after doing this quantization step that we explained last time, how the coefficients would look like. What will happen is, as we said, that the high frequencies, if the high frequencies are here, okay, this is where this area now, the one on the right, this area, now includes all the high frequencies, because remember we said this is where the origin is, and this is the increase in the horizontal frequency, and this is the increase in the vertical frequency. So all of the high frequencies will be on the right bottom and the bottom right corner of this space. Okay. Now, given that we are the high frequencies are given values that are either that are represented using only 1 bit, so either 0 or 1, you will have a lot of zeros, because in general, even the high frequencies wouldn't, even if they are present in an image, they wouldn't be actually that high in terms of the coefficients that they have. So most probably you will have lots of zeros, like something like this, 0, 0, 0, 0. You'll have a lot of zeros here. And the area in the middle will also have some zeros, but not as high as the area on the right. So here you will have also some zeros and so on. So what we do is that in order to get more compression, when we are storing those coefficients after you apply DCT, after you do the requantization, is that you actually try to sort or order the coefficients such that the zeros will come right after each other through that zigzag sequence. So the first coefficient that you store is this one. Okay. Second coefficient you store is this one. The third one, normally this is a matrix. You should normally you would store it as row by row and so on. No, but this is not what's done actually in the JPEG. You store this one, and then this one, and then this one, and then this one, and so on. You keep doing this. Why? Because by doing this, the end of this sequence will be the frequencies that are here, which are the high frequencies. So you'll have a high chance of having long sequence of zeros. That long sequence of zeros is encoded using the run length encoding. So you see, like we explained what run length encoding, and we saw how it can actually reduce the number of bits needed to store anything. Now we do the JPEG compression first. First step, do DCT. Second step, do the quantization. You get lots of zeros. Now, okay, can we do store this in a smart way such that we will have more compression? Yes, we do this zigzag ordering, like you store this coefficient, this one, and so on, and then you will have lots of zeros at the end, and then those zeros are encoded using run length encoding. Okay, so that will give you more compression. Also, the non-zero coefficients, so the ones that are not zeros, that will not be encoded as run length encoding, we actually compress them using Hoffman coding. So based on how frequent they appear, they are actually compressed using the Hoffman coding method that we also explained as a lossless compression method. So it's like you're using the Hoffman coding, you're using the run length encoding. Both will cause actually a reduction in the number of bits needed, and also you are actually before that doing the quantization step that will also reduce the number of bits needed. Okay, so this is the main idea of the JPEG compression. We talked about this slide before, and we saw, okay, that decompression, if you would like to decompress the JPEG stored image, decompression is performed by reversing the process that we talked about. We use the inverse DCT to recover the image from its frequency domain representation, and you reverse all the processes. Okay, this is, as we saw before, an example for an image, and it's JPEG compressed image, and we say here that the compressed image may exhibit compression artifacts, including blurring and visible edges at the boundaries between the 8x8 pixel blocks. Remember, we said that it's like if you have an image like this, you divide it into blocks. Each block is 8x8, and you apply all the process, DCT, zigzag ordering, run length encoding, all of that for each block separately. Sometimes when you look at the JPEG compressed image, you'll find it looks like you have those blocks. If you zoom in on this image, you will see those blocks. Okay, and especially this will appear at low quality, like low resolution images. Okay, so these are some issues in JPEG compression that were later on overcome actually using other techniques, as we will see later. So after the JPEG compression, there was another improved version of it called the JPEG 2000. It was made in the year 2000. It improves on JPEG in many areas, including image quality at high compression ratios, and it can be used actually losslessly as well as lossly. What are the differences? We're not going to talk much about this, just briefly. So JPEG 2000 compression, the image is divided into tiles, similar to the blocks, the 8x8 blocks that we talked about in JPEG, but these can be of any size and up to the entire image. It uses, instead of the discrete cosine transform, it uses something else called the discrete wavelet transform. Discrete wavelet transform, or DWT, this is how it looks like. If you have an image like this one, the idea of DWT is that you obtain multiple scales of the image. This is the original image, and you see like different versions of the image with different resolutions. Through getting two sets of coefficients, ones that are called the approximation, and the others are called the detail coefficients. And these ones are used in the process of the compression. Okay, so those coefficients in the wavelet transform that called detail coefficients are quantized and then lossily compressed using something called arithmetic encoding. Regardless of the details, because we wouldn't have time to go into the details of this, but just look at the comparison. This is the original image, the same one that we saw before. This is after you compress it using JPEG 2000 and decompress it. This is what you get. This is what we got with the JPEG. Now, comparing these two images, you can see that this one has a better quality. One thing to note, for example, look at this dot here, the blue dot that we have here. It wasn't that visible here, it's more visible here. Look at the edges in this area. See how you have here some distortion of the edges, but here the distortion is much less. So that's why the JPEG 2000 gives you a better quality in terms of the quality of the image. Okay. Alright, so this actually is the last method that we will talk about in terms of compression in images. We next talk about compression in videos. Okay, so for video compression, how we do it. So let's talk about the concepts of video compression. So the input to any video compression algorithm consists of a sequence of bitmap images. Those bitmap images represent the frames that are stored in the video, because any video, as we said before, consists of frames. So the input to the video compression algorithm would be that sequence of frames. Now, there are two ways in which this sequence can be compressed. There is spatial compression and there is temporal compression. What's spatial compression? This compressing each individual image in isolation using image compression techniques. Like, as we will see, you take one frame and compress it using JPEG compression, for example. Okay, so every single frame is compressed as if it's a single image. So this is what's called spatial. Spatial, the term spatial here is coming from the idea that you have, we're talking about space. Okay, now temporal compression is different. We're compressing frames by only storing, and we will see examples of this, where by only storing differences among successive frames. So temporal here means that we take time into consideration. So you're looking at the successive frames and try to make use of the idea that there might be repetition between frames and therefore we don't need to store each single frame. Maybe we can only store the differences, as we will see. Spatial and temporal compressions are actually used together in most video codecs that are currently available. Okay. So let's see examples of both. So we start first by spatial compression. It's the technique of compressing video sequences by applying JPEG compression to each frame, and this technique is called the MJPEG, okay, where M here stands for motion JPEG. So this is one technique. Take every frame, compress it using JPEG compression. This is called MJPEG. Now, before that, chrominance subsampling, if you remember, we talked about this before in video representation. Chrominance subsampling is nearly always applied before any compression, and that by itself will cause actually compression. This is, for example, 4 to 1 to 1. Every 4 pixels, you have 4 grayscale representation, the Y, and then 1 CB and 1 CR representation. There is also something called 4 to 2 to 0. The idea here is that every row you either have the CR components twice or the CB components twice. This is also used. In any case, both, whether this one or 4 to 2 to 2 or whatever, all of them, they will achieve compression because you're not storing for every single pixel, you're not storing the 3 components. You're only storing here, for example, for every 4, you're storing the 3 components for the first pixel, and for the next 3 only the Y, the luminance component. Okay. DV compression is purely, and DV is one digital video. This is one standard for video. This is purely spatial, and it extends the JPEG technique to compress video files. As we explained, it uses the MJPEG technique. Okay. So spatial compression is not really something hard to do. Let's now talk about temporal compression, which actually achieves more higher compression ratios. So all modern video codecs, they use temporal compression to achieve higher compression ratio or better quality relative to the MJPEG, the motion JPEG that we explained. Temporal compression works by computing the difference between frames instead of storing every one in full. So let's look at this example. This is one frame, and this is a second frame that was taken very short amount of time right after this one. So these are both part of a video. Now, if you look at this frame and compare it to this one and compute the difference between them, just the difference here, you're subtracting, doing just regular subtraction, every pixel minus the previous pixel. Okay, this is actually what you will get. So for example, you look at the background here. See that the most probably between this frame and this frame, if the difference time between them is something in milliseconds, most probably the clouds wouldn't have moved between this frame and the next one. So there would be no difference. Every pixel, if you take that pixel, compare it to this pixel, they will have exactly the same color. That's why when you take the difference between them, you get actually 0, black. Okay, same thing for the trees, same thing for the ground. The ground would not change between one frame and the other one. The only change will happen if that character, that person, actually moves between this frame and the next one. So this part, because of the wind, might be moving fast. And this is what you see here. You only see, when we did the difference, black means 0 difference, and colored value indicate that there is some difference at these locations. Okay, some of the differences are high, some of the differences are not that high, but the main idea here is that if you have this, if you can compute the difference between two successive frames, then why not, when you are storing the video, you store this frame, and then you don't need to store this frame. You only store the difference between this frame and this one. So then, when this is what you store. Now, if you are playing back this video, this frame will be displayed first, and then when you are displaying the second frame, you're not going to display just the difference. What you will do is that you will take the difference and add it back to the original frame to get the second frame. Okay, so if this is obtained by subtracting one from the other one, then we can recover this one by just taking this and adding it to the difference frame that we have. We call this the difference frame. Okay, so this is the main idea. Now, if you think about this, how would you store that? Now, this frame, it has a lot of zeros. Okay, so this is one thing. You can, as we mentioned before, you can compress the zeros using run length coding, for example. Okay, and one other thing, the differences between these pixels, most probably they would not be that big, you know, like, because again, the difference between this frame and the next one, it's a very tiny difference in terms of time. So therefore, the change in the color of the pixels wouldn't be that much, and therefore the amplitude of the differences would be small, that can even be represented with a small number of bits. So now, by storing only the differences, we are saving a lot in terms of storage in that case. Okay? Okay, so actually what we just described is something that's used in something called MPEG-1. MPEG stands for Moving Picture Experts Group. This is very similar to the JPEG, the group that developed the JPEG technique. There is MPEG. The MPEG-1 standard represents the first systematic, actually, temporal compression standard. So how is it done in MPEG? How does it do the temporal compression, making use of the differences? In the MPEG has some terminology. It calls, it has two types of frames. We have frames that are called the I pictures and frames that are called the P pictures. I pictures, they're called I's for intra, and they represent the reference frames that are only spatially compressed. So these frames will be stored in full, but using spatial compression, like using JPEG, for example. While P pictures, these are called, P is for predictive, and these are computed using the idea of difference from a preceding I or P picture. So let's have an example. These are 4 frames taken from a video where you see this person is actually jumping from above. In this position, or in this frame, he's here. Second frame, he's here. Third frame is here. Fourth, he's here. So he's just like a falling down, actually, in that case. Okay. Now, how are we going to store these 4 frames in MPEG-1? The first frame, this is like the first frame in the scene. You have to store it because you don't have a reference for it. So this one is stored as an I frame or an I picture. Now, all of the 3 successive frames are actually predictive, meaning that you can actually get this frame from this one. How? By only storing the pixels here that will be changing relative to this one. So for example, this part here, which is the mountain, this will not change between this frame and this frame because the camera is static. In that case, the camera is not moving, and of course the rocks here will not change. This is, of course, can be measured by comparing the 2 frames, but in any case, these will not actually be not be changing across frames, and therefore there is no need to store this part of the image, whether for this frame or this one or this one. What you need to store for this frame, only the pixels that will be changing, and these are like, this is the waterfall that we have here. Of course, the water, because it's falling, it will be changing, the pattern will change. So we are storing this part, and when comparing this frame to this frame, the difference would be that person, in this frame he was here, in the second frame he is here, okay? So he fell a little bit, and therefore we have to store from this frame where that person is located now. And also we have to store actually from this frame the location or the area that was covered by the same person in the first frame. Why? Because when this person falls a little bit down, he actually uncovered an area in this frame, and therefore this needs to be stored, because you wouldn't be able to get, you know, like if that person left this area and moved down a little bit, the area that he uncovered, we cannot get it from this frame because it was covered, but we can get it from the second frame, the P frame. So therefore in the P frame we have to store the location of the person and the area that was actually uncovered by that person. And this is mainly done by just subtracting the two frames, doing this minus this. You will get that automatically, okay? So all of the white areas here are pixels that no need to store. We don't need to store them. We can get them directly from the first iframe. In the third frame, this is another P frame that is actually also predicted from, in that case, it's actually predicted from this frame. Again, we are storing the waterfall part because this will be changing between this frame and the next one. And then between this frame and the next one, this person moved from here to here, so we need to store this area, and the same thing for the fourth frame. So this is the idea. These frames are called P frames. These are predictive frames, P pictures. Frames or pictures that can be predicted from an intra frame, a frame that was a reference frame that was stored in full. Okay. Now, by only storing these pixels and these pixels and these pixels, and the white ones are not stored, you are actually saving a lot in that case. Okay. So actually, one other thing, in addition to the idea of storing the predictive frames relative to the intra frames, is another thing that also can enhance the compression, something called motion compensation. And what is motion compensation? It's the technique of incorporating a record of the relative displacement of objects in the different frames as a motion vector. First of all, this technique is suitable, very suitable for actually vector graphics type of animation. Okay, and well, I'm gonna explain why. But let's see the example. Let's say we have this frame 1 and this is frame 2. In frame 1 we had this fish here, and in frame 2 the fish has moved a little bit to the front or to the right. Okay. So one thing we can do is we can represent that information, or represent frame 2 relative to frame 1. Frame 1 would be an intra frame. How about frame 2? Frame 2 would be a predictive frame. Definitely you can predict this frame from this one. How? If you compute the difference between these two frames, you will find that, you see like the area in black here. So this is a little bit different from before. Before, the black or the white represented things that you do not need to store. Now here, just to explain the idea, what is shown in black is what you need to store. Okay, just this is to avoid confusion compared to what we had before. What's now shown in black is what you need to store from the predictive frame relative to the intra frame. So let's see this. This is frame 1, the fish is here. Frame 2, the fish is here. If you compute the difference, this minus this, the background, all of this part, for example, this area here is the same as this area here. So when you take the difference, they would be 0. So meaning that there is no need to store them. You can get them from frame 1. Okay. But the difference, or the area as well, the difference will not be 0, is related to the location of the fish in frame 1 and the fish in frame 2. This is actually shown here. So what is shown in black is this is what you need to store from frame 2. Okay, if you have these pixels shown in black from frame 2 and you have frame 1, you can draw frame 2 easily. Why? Because this, if you take this part from frame 2, it would be around, like, let me draw here. We're talking about this area here, something like this. Okay, now if you take that from frame 2, okay, and just put it on top, take that and put it on top of frame 1, you get frame 2, exactly the whole frame 2. Why? Because in frame 2, the fish is here, so this is what is shown here, and in frame 1, the fish was here. So the area that was covered by the fish in frame 1 is now uncovered in frame 2. That's why you need also to store this area from frame 2, so that you can get this frame completely from this one. So if I'm storing these pixels from frame 2, I can just take them and put them on top of frame 1. Okay, so they will be put here, and that will give you frame 2 because you're putting that over here, so you get frame 2. The rest is taken from frame 1. So this is what we explained before, just computing the difference and storing the difference. So as mentioned here, this is without what's called motion compensation. Pixels shown in black is what needs to be stored in the difference frame. Now there is a better thing that we can do, which is using motion compensation. So what's the idea of motion compensation? Let me erase this part. Okay, so what motion compensation is that if this is the fish in frame 1, and if we know that between frame 1 and frame 2 the fish has moved from this point to this point, then what we can do is the following. We can actually store the motion vector. Like we can say that if the center of the fish was at this point, the center of the fish moved to this point here. Moved to this point here in frame number 2. So we can just save that vector, and that vector is if the fish is an object, then that vector would be just an x and y. So for example, if x is the x coordinate, y is the y coordinate, it seems that the fish has moved horizontally, so there is no change in y, but x, for example, would be 20. It's like you move 20 pixels to the right. So you can store this, just these two numbers. Okay, this is called the motion vector. Okay, and in addition to what? In addition to when the fish moved from this point to this point, there is some part that was uncovered by the fish. Now that, okay, let's assume we're doing this. We're taking this fish and moving it here. So how about this area? Where would we get its value from? That is what we need to store from frame number 2. So what is shown here in black is what you are going to store from frame number 2 in addition to the motion vector. So by storing the motion vector and storing only those pixels from frame number 2, you can draw frame number 2 given frame number 1 by moving the fish to the right and putting those pixels from frame number 2, put them on top of frame number 1, because when the fish moves, you'll have a blank area here. That blank area would be filled by those pixels from frame number 2. Okay, so this is actually what is written here. So we're saying that this is what we call motion compensation. So with motion compensation, we only need to store the displacement vector, the motion vector, how the fish has moved, and the pixels shown in black from the second frame. Now, if you compare this, what you are storing from frame number 2, in this case with motion compensation, to what you are storing from frame number 2 without motion compensation, you're storing here less number of pixels. You see here, all of these pixels in black need to be stored from frame number 2. So the number of pixels that you need to store here is much higher than this. Okay, so in addition to these pixels, you are only storing 2 additional numbers, which is the motion vector. So obviously, the number of pixels that you need to store from frame number 2 using motion compensation is much less than what you need to store without motion compensation, and that's how this method can achieve higher compression ratios. Okay, so this is what motion compensation actually is, and how it can save more in terms of the number of bits that need to be stored. Okay, now can we do even better than this? In fact, yes, there is something else in addition to the predictive or the difference representation, and in addition to the motion compensation, we have something called the B pictures. So we have the I pictures, we have the P pictures, and we have something called B pictures. And B here stands for bidirectional. So this one It's trying actually to do more than what we can do with the predictive coding, even with with the predicted pictures, even with motion compensation, which uses the bidirectional pictures. They use the following pictures as well as the preceding one as the basis of frame differences and motion compensation. So this bidirectional picture or bidirectional frame, it's not only going to rely on the previous frame, it will actually also take into account the next frame and try to see if we can make use of the previous and the next frame to save more in terms of storage. Let's see an example. So this is frame number 1, this is frame number 2, and this is frame number 3. Now the addition here is that we have an additional fish, a small fish that started to appear. Okay, so if we are going to let's focus on that frame 2. Let's see how frame 2 can be predicted from frame 1, and then we'll see how it can be predicted from frame number 3. So if you are predicting frame 2 from frame 1, and let's assume we are using motion compensation, then what you actually need to store from frame 2 with motion compensation relative to frame 1 is the following. First of all, this fish was here in frame 1 and it moved to this location in frame 2. So as if we have a motion picture from this point to this point. Okay, so a motion vector, I mean. So we're going to store this motion or displacement vector. Okay, now when the fish moves from here to here, there is an area that will be uncovered, as we explained before, and that has to be stored. This represents here what you need to store from frame number 2. So this is what you will store from frame number 2 in order to get this image from frame number 1, assuming that we have motion compensation for this fish. How about the small fish? Actually, the small fish will be inside this area here, the area that was actually covered by the first fish in frame 1. Okay, so therefore, to get this frame 2 from frame 1, we will store these pixels from frame 2 in addition to the displacement vector of the big fish. Now, this is what's written here. So with motion compensation, frame 2 can be obtained from frame 1 using diff1. Now let's see, can we obtain frame 2 from frame 3? Although frame 3 happens in time after frame 2. In fact, yes, you can get frame 2 from frame 3. How? In both frames, the two fish, they appear. The small fish actually moved between frame 2 to frame 3. It's like moved a little bit to the left. It's now here. And the big fish was here in frame 2, and now it's here in frame 3. It moved a little bit to the right. So if we're doing motion compensation, then okay, what we will do, if we're predicting frame 2 from frame 3, we will store the displacement vector of the small fish, which will probably be a little bit to the back, like this. Let me use a different color. Let's see, we can use orange. So going back a little bit like this. And for the big fish, so now this is the location using that motion vector that I draw here. This would be the new location of the small fish, but in frame 2. How about the big fish? If it moves a little bit to the back, you will get it where it is in frame number 2. Okay, so we now have two motion vectors, one for the small fish, one for the big fish. Now when this fish goes back and this one goes back, this fish, when it goes back a little part will be uncovered, and that needs to be stored from frame number 2. And when the big fish also goes back to get its location in frame number 2, a small part here will be uncovered, and this is what you need to store from frame number 2. So now, by representing frame 2 relative to frame 3, although frame 3 happens after frame 2, but this method, okay, we are making use of that. And so this is what we need to store. We need to store this from frame 2, this from frame 2, in addition to the two displacement vectors. So frame 2 can be also obtained from frame 3 using diff2, okay, which gives smaller representation. The number of pixels that you are storing, the number of black pixels that are shown here, actually this is less than what you have in diff1. But there is actually something even better than this, which is, can we predict frame 2 from frame 1 and frame 3 combined and get something better? So with motion compensation, frame 2 can also be obtained from frame 1 and frame 3 using diff3, which gives much smaller representation. So how? Let's see. If you're predicting frame 2 from both frame 1 and frame number 3, this is what we will do. From frame 1, we will store the displacement vector where this fish has moved from this point to this point. This is the new location of the big fish. And then from frame number 3, we're going to represent the motion vector of the small fish going from this location to this location. Now, when you look at this frame and this frame, so now let's think about this a little bit. So now by this moving backwards, you get the fish here, and by this moving forward, you get the big fish here. So now you have the two, the big and the small fish in place. Now, what are the additional pixels that you need to store from frame number 2 to get this? In fact, what you need to store from frame number 2 is only this little part. Why? Because when this fish is here and this fish is going back, the only part that would be left that you do not have any representation for, this is the part where in both frames this was actually covered. So what was covered in frame 1 and frame 3, both of them, actually you see where the big fish here and where the small fish here, the only part that was covered in both cases by the big and the small fish is actually this little part, okay, this part. So therefore, this is what we only need to store in frame number 2. If you store this and store the motion vector for the big fish, the motion vector for the small fish from frame number 3, you will get this frame, right? There is nothing left. Okay, this fish will be here. Okay, we have it in place. And the small fish will go back. It will be here. Okay, and what else? Okay, we need to store just this little part from frame number 2. Now we have all of the parts that were covered in frame number 1 and number 3. You get that from frame number 2 and you have the fishes in place. How about the rest? The rest you can get from, for example, frame number 1 or frame number 3. It doesn't matter, whatever, which one of them, because the rest is constant actually in both cases. Okay? So this is the idea. With motion compensation, frame 2 can also be obtained from frame 1 and frame 3 using diff3, which gives much. Now, if you think about how many bits you need to store in that case, you only need to store these little bits. That's it. You don't need to store anything else. So this is the idea of bidirectional pictures. This frame is now bidirectional. It's taking information from frame 1 and from frame number 3 and keeping little part from frame 2 that cannot be obtained from frame 1 or frame 3. Okay? The background here is what's common between the two frames. You can check what is common between frame 1 and frame 3, and this is what you can actually keep in frame 2 in that case. Okay, so this is what bidirectional. So now we talked about 3 types of frames. We talked about the intra frames or the intra pictures, which are stored in full. The P pictures, which actually have to be stored relative to a previous frame. This is what a predictive frame is. You only store the frame or the picture based on a previous picture. And the bidirectional picture, which you store the picture based on a previous and a subsequent or another frame that will come afterwards. This is what bidirectional prediction is. Okay? Okay, so given this information, so let's see how the MPEG actually standard works. A video sequence in MPEG is encoded as a group of pictures. We call it a GOP. If B pictures are used, a GOP may have to be reordered into display order. We'll talk about this later on. So this is actually how the MPEG orders the frames. The first frame is called an I frame. As we said, the first frame has to be stored in full. There is no way you can not store it. And then the next 2 frames are bidirectional frames. B here stands for bidirectional, where this frame, frame number 2, is going to be predicted from frame number 1, the I frame, and a P frame that comes later on. As you can see, the P frame, so the arrows indicate what each frame will be taken from. So B frame will be taken from frame number 1, B frame number 2, and from the P frame number 4. While the P frame, the predictive frame or the predictive picture, has only to be predicted from a previous one. So this frame will be predicted from this one. So the P frame is predicted from this I frame. Okay. This frame is also B1, a B frame that will be predicted from the previous I and the preceding P. Now, next, after this P frame, we will have another 2 bidirectional frames that are taken from a previous P and an upcoming I, as you can see here. So this is called the GOP, a group of pictures. It has a sequence of I, B, B, P, B, B, and then that sequence keeps repeating afterwards. So we will have to repeat this. So we have I, B, B, P, B, B, and so on. Now here we have another intra frame. So this is a new frame that will be stored in full. Those two B's, similar to these two B's, will be predicted from the previous I and the upcoming P, and so on. Now there is one little issue with this. If this, let's assume this MPEG video will be actually sent over the internet and you have to play it on your computer actually as soon as it comes. Now there is an issue here, because if we send the frames in that sequence, like we send this frame first and then send this one and then send this one and send this one, there is a problem. The first frame, when it's sent, you receive it, you can display it. Now the second frame to be sent is a B frame. Now if this is sent to you and before receiving frame number 4, because obviously in that case it will be sent later on, then how are you going to display this bidirectional frame? As we said before, to display a bidirectional frame, you have to rely on a previous and an upcoming frame. So you have to have, before, to be able to display that frame, you have to receive first this frame and also this one. But if we send the frames from, let's say, from a server to your computer, we send this frame and then we send this one, you will get this one, but you will not be able to display frame number 2, because to display from frame number 2, you have to have this one and this one received, which are not yet. And then if we send this one, then there is an issue here. So in fact, the MPEG frames, or an MPEG video, when it's actually being transmitted, the frames will be transmitted not in the same order of their appearance. They are transmitted based on the order that will guarantee that when they are displayed properly. So we send this frame first. This is the first frame to send, and then the next frame to send is frame number 4. Why? Because these two, frame 2 and 3, they need frame 1 and 4 to be able to be drawn in front of you, and therefore we send the frame 1 first and then frame 4. Now by sending this one and this one, we can send these two, but now this one, when it's received, it's not displayed, and this is the idea. Frame 1 is received, it will be displayed. This one will not be displayed. Okay, this one will be displayed right after frame number 1, because now we have this, and then this one will be displayed, and then this frame which we received earlier will be displayed as the 4th one. So the display order would be this, but this is the sequence in bit stream order. Now after sending this, the next frame to send has to be this intra frame. Why? Because these two B's rely on this predictive frame, frame number 4, which we already received, but it also relies on frame number 11. So we have to send the frame 11 first, and then send frames 5 and 6. Again, frame 11, when it's received here, it will not be displayed, just be stored, so that we can predict frames 5 and 6. They are displayed, and then frame 11 will be displayed in that case. Okay, so this is the difference between the MPEG sequence in display order and in bit stream order in the transmission order. Okay, all right. So this was actually the story of the MPEG and how it uses both temporal and spatial compression. MPEG 4, by the way, part 2. We have MPEG 4 part 14 currently. This one uses the global motion compensation and subpixel compensation to improve the quality of MPEG 1 and MPEG 2. By the way, when you store a video as MP4, MP4 is the extension of the file. This is like you're storing using the MPEG 4 compression technique. Actually, this video, when it was uploaded to the system online that you're watching on right now, it was uploaded in the MP4 format because it gives the highest compression ratio. There's also other standard like H.264 ABC, and these add extra techniques, including variable size transform blocks, micro blocks, deblocking. All of these are just improvements on the MPEG-4. Windows Media 9 also incorporates similar improvement. Finally, all modern codecs that are used for video compression, they produce excellent quality at 2 megabits per second and higher, meaning that every second of video you can actually store it in 2 megabits, 2 million bits for every second of video, or even higher than that, which is a good compression ratio. At the same time, the quality is preserved. Okay, so this ends actually the compression topic, where we talked about image compression, we talked about video compression. How about audio compression? This would be in the next topic, because next topic we talk about audio, and then we will also talk about audio compression. Okay. All right. So let's move now to the next topic, which is audio. So next topic is audio. After we covered images and video and compression, now we move into the audio topic. So let's first talk about the nature of sound and how we as humans hear things. So sounds are actually produced by the conversion of energy into vibrations in the air or some other elastic medium, which are detected by the ear and converted into nerve impulses, which we experience as sound. Let's talk a little bit about this idea. So this is actually the outer side of your ear. The main thing about sound is just change in the or vibration or the pressure of the air around the ear. Now that air would come into your ear inside here, and it hits something here called the tympanic membrane. This membrane is something very flexible that when the air pressure comes in here, it moves. Now the movement of this tympanic membrane moves some device inside your ear, and that thing will actually cause motion in this. This one is called the cochlea. The cochlea is something inside your ear. The cochlea has a nerve. You see this orange thing? This is called the nerve. So what's the idea here? What this actually nerve does is that when the sound comes in, tympanic membrane moves, the movement of this membrane will cause that nerve to move itself. However, this nerve, the movements that happen in the nerve actually depend on the frequency of the sound that you're hearing. So for example, if you're hearing something around, let's say 1000 hertz, you see this is how the membrane looks like, or the nerve looks like. This part, you see here 1000 hertz, this part only will move. This is the part that will move due to that frequency in the sound. If you hear something around 5000 hertz, this part is the part that will move. 4000 hertz is so on. So what's the highest value that we have here? It's around 20,000 hertz. And that's why we say that humans can hear up to 20,000 hertz. Why? Because in fact, the end of this nerve is at 20,000 hertz. If you have a higher frequency around you, the nerve will not move. And now, if that nerve is not moving, that nerve, so how do we hear sound? The nerve has little cells connected to it. And those cells, when the nerve moves, those cells produce like small tiny electrical pulses. Those electrical pulses, they go into your brain, and this is how you feel sound. Okay? So now if the membrane does not move, you will not hear anything. And that's why the maximum frequency is 20,000 hertz. If you have like a sound of 30,000 hertz, you will not hear it because that nerve is not going to move, and therefore no impulses or no little electrical signals, those tiny electrical signals will not be generated, and therefore you will not experience sound. Okay? So this is how we actually hear sound, we as humans. Okay? Now thinking about this, maybe you didn't know this before, that your ear has a device, the cochlea, that can analyze the frequencies in the sound. It's doing something very similar to what? To Fourier transform. It's like you have something in your ear that does Fourier transform. Takes the sound is coming as a signal, and it can identify the frequencies that are in the sound. So you had a Fourier transform in your ear all that time and you didn't know. So I'm just telling you that information maybe right now. Okay, so this is how we hear sound. Let's see how we can digitize sound, and this is what we are going to cover next. So something related also to the nature of sound is a sound's frequency spectrum. This is a description of the relative amplitudes of its frequency components. One thing about our ability to hear is that it actually deteriorates with age. So the human ear, as we said, can detect sound frequencies roughly in the range from 20 Hz to 20 kHz, though the ability to hear the higher frequencies is lost as people age. So as people age, they cannot hear the high frequencies well. You see, like, let's look at this curve. On the y-axis we have the hearing loss, on the x-axis we have the frequency. This curve is the ability of people who are 20 years old to hear sound. So they have no loss in hearing in all of these frequencies, while in 8 kilohertz, a little bit, they cannot hear it that well. Now, at 40 years old, the hearing loss for the 8 kilohertz is higher, the high frequency. At 60 years old, you see here, at 90 years, it's like even they cannot even hear the 8 kilohertz. And even the lower frequency, like 1 kilohertz, 2 kilohertz, you see the deterioration is higher. So as people age, their ability to hear the high frequencies is worse, but the low frequencies are relatively okay. Okay? Now, what is a sound waveform? A sound waveform shows how its amplitude varies over time. This is, for example, a waveform for sound for someone who's talking. Silence would appear as very low amplitude signal, while talking you'll have high amplitude. So the high parts here represent when someone is talking. Okay. Another example is recorded songs. They combine characteristics of both speech, where you have parts that someone is talking, parts that are silent, and then music as well. You can see here, because music, when it appears, it will be strong. So you see, like, it's not like you have talking and then silence as when people talk. No, we have also instruments playing, and that's why you see this is how a sound waveform would look like. Now, this is another example, something from nature, like seashore sound. This is actually, imagine you are on the beach and there are waves. So when the wave comes, it breaks, and then when the water splashes, this is what you see. So this is actually the signal representing wave breaking, and this is where the splash happens, much higher amplitude. Okay. Now, how do we digitize sound? And this is what we need to focus on. So similar to an analog signal, sound is digitized through sampling and quantization, the same procedure we talked about before. Since the limit of hearing is about 20 kilohertz, we need a minimum rate of 40 kilohertz. Why? As we said, sampling theorem states you have to have more than, or at least, twice the highest frequency you can have. So given that the highest frequency we hear is 20 kilohertz, then the sampling rate, in order for anything not to occur, needs to be at twice that, which is 40 kilohertz. That's why the sampling rate of audio CDs is 44.1, way above double the highest frequency. Audio delivered over the internet, sometimes it's sampled at 22.05 kilohertz, while speech is sampled at 11.025. Why 11.025? Because when people talk, they can hardly do the very high frequencies with their vocals, right? When people talk, if you look at the frequency spectrum of talking, most probably it would be lower frequencies. People cannot do those very high frequencies unless they're like, for example, an opera singer, for example. So the singers of opera, they can, with their vocals, they can do actually things like very high frequency. But speech, normal people wouldn't do that. So that's why 11.025 kilohertz, which means that the highest good frequency you can represent is half that number, 5.5 kilohertz. This is what's used for speech. For internet, we use 22.05. Again, this means that the highest is 11.025. At the same time, or for example, as you reduce the number of samples or the sampling rate, you can actually save in terms of storage. Professional recording devices sometimes use double or 4 times the CD sampling, 96 kilohertz or 192, just to get to make sure that there is no aliasing at all, and this is the whole idea. Now, CD audio also, in addition to using a sampling rate of 44.1 kilohertz, they use a quantization of 16 bits per sample, and that gives, if you have 16 bits, this gives you about 65,536 different quantization levels. to maintain small file sizes. A smaller number of bits is used, where 8-bit sound is the minimum acceptable. Instead of 16, we go down to 8. Of course, when you do this, when you use small number of bits, this causes what's called quantization noise. So if this is a sine wave that is represented with 16 bits per sample, if you go down to try to quantize it into less number of levels, here we're quantizing that into 1, 2, 3, 4 levels, meaning that instead of using 16 bits per sample, you're only using 2 bits per sample. This is how a sine wave would look like. It's like constant sound, and then this is sample and hold kind of reconstruction. Constant, 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 so on. So therefore the quality would be much lower. So one thing here that we can do to improve the quality of the undersampled sound without increasing the number of quantization levels is to use dithering. You remember we talked about dithering before in indexed image and how we can use it to simulate colors that do not appear in the color table. We can do the same thing here, but actually on sound. So in dithering, noise is added to the original sound before quantization. If this is the sine wave that you want to represent, and you need to represent that sound only using a less number of quantization levels, what you do is that you add noise, random noise, like random values on the sine wave. And then you take this sine wave with the random noise and you apply dithering to it. So what happens is, this is how it will appear. This is how the sine wave will appear. It has ups and downs. Instead of having a constant value as we saw in the previous slide, it will have ups and downs. So how would that improve the quality of the undersampled sound? Let's look at that video.
Okay, in this video let's look at dither. Now what is dither and when do you use it? Those are the first two
So
questions
this guy is actually going to explain what dithering
so what is dither?
and we'll show you
Dither
the
is just
example
simply
how it
noise.
happens.
When do you use it? Well, you use it when you're reducing the bit depth of digital audio. Okay, so let's see how it works and why we use it. I'm going to start off with a basic sine wave here. I'm just going to play it to you briefly.
This is actually how a sine wave sounds.
What I'm going to do is add a bit reduction plugin. At the moment it's 24-bit, but I'm going to reduce this, and I want you to listen and watch what happens when I do.
So he will reduce the number of quantization levels. You see in the bar. Okay, he's reducing it here, and listen to the sound.
Okay, so notice that the distortion becomes quite obvious. You start getting all these other harmonics that have been added, so from lower harmonics up to higher harmonics, and it just overall has a kind of a nasty tone to it.
So you hear that distortion.
This is called truncation, where we simply convert 24-bit to 16-bit by removing the lowest 8 bits. However, it creates a byproduct of that, a tiny bit of distortion.
Add this noise to the sound.
Okay, so how do we fix that? Well, let's just try adding some noise. Now on this channel here, I'm just going to insert a noise plugin.
So this is how he's adding noise.
Just regular white noise. Now I'm going to blend this noise with our original sine wave and watch what happens to the distortion.
Okay, so he's adding the noise. You hear that? Now you can hear that the sine wave is getting to the normal in addition to the noise.
Eventually the noise actually masks the distortion. It's basically trading one set of noise in favor of another. So what we're doing is we're adding noise to avoid distortion.
Okay.
And honestly, it's as simple.
So this is the idea. It's like you're adding noise to the signal to trying to reduce another type of noise. Okay, so this is what dithering is actually all about. Okay. Alright, so we're gonna stop here and we're going actually to continue this in the next lecture. Okay, alright, thank you and talk to you soon.